Yeah, Mr. Sand, I want to talk to you a little bit about um, atomic theory. This is going to span a couple topics that include the topic that I have that's called electrons to planets, and the other one that says neutrons plus Bohr. This is going to really cover both of them. This is kind of the part in chemistry where we get to talk about the history, like the history of discovery. And I think it's important to include this because uh, because because chemistry and science in general just doesn't stay put. It doesn't stay stagnant. Things happen all the time. If you have a theory that's proven over and over and over again, if it's something comes up that doesn't agree with your theory, then you have to revise your theory and into something else. And theory is something that's a little bit more rigorous than what you normally think of as, oh, it's just a theory. In science, theory really means something that's been proven over and over and over again. So this kind of change in theory and science theory is major. And so that's why I think it's important to go through some of the big changes that happened with this atomic theory. At first, you just have we had the idea that, well, even before atoms, people thought things were made up of very small substances, small things. Atoms were fought over and over and over again, and eventually they were accepted as an idea that was true as the smallest indivisible objects. And then later on, you could split the atom, and you could get lots of energy from that. But we're not going to go into that part. We're just going to talk about atoms right now, so the history of atoms. First of all, I want to talk to you about this guy called J.J. Thomson. J.J. Thomson was important. J.J. Thomson was important because he discovered electrons. I'm not going to go into the details of this because it's not relevant, but he did notice something about those electrons. He noticed that they were small, that they were smaller, much smaller than any atom ever recorded. Okay? They're very small. He also noticed something that was weird. You noticed that they had a charge. So they had a charge. It was a negative charge. Okay? All right. So here's a little example of a cathode ray tube. A cathode ray tube shoots little electrons, as you can see right here. And here's another teacher showing it. I used to have one of these in the chemistry lab. You just hook up an electrons, or hook up this cord right here to a power outlet, and then electrons are rushed through here, and you can show them through this little phosphorescent screen that lights up. And if you put a little magnet on top, look at that, it's repelled this whole, oh, that's a weird kind of effect. Sometimes you have these very bizarre kind of scattering effects where they kind of reverberate and bounce around each other. Oh, this is cool. He's showing the different angles of it. So he's just pressing down right now, and then it's repelling. So they figured out that these things, whatever they were, had a negative charge, and they were very, very, very small. Smaller than atoms. So if you put these facts together, I'm going to put up these kinds of steps in his logic here. He knew that overall, the atoms didn't have any charge. Overall, atoms were neutral. By the most part, they were neutral. They didn't have a charge to them. He also knew that electrons were parts of, or he guessed that electrons, and I'll just abbreviate electrons with this little e and a little negative sign, electrons were smaller than atoms. And he knew that electrons were negatively charged. With these three pieces of information, he came up with, and you might be able to think of this too, what the result would be with these three steps in logic. He knew that atoms were neutral, electrons were smaller than atoms, and most likely a part of them, and he knew that electrons were negatively charged. So according to J.J. Thomson, he thought that an atom must have something positive inside of it to balance out those negative charged electrons. So, therefore, he came up with this idea that there were these little negative electrons inside something like an atom. And I'm going to draw the atom as a big object. I'll draw it as a big teal object. Here's the atom. The whole thing would be an atom. And he thought that this atom, the other stuff that made up the atom, that was not the electrons, was a bunch, what the stuff I'm drawing right now, is a bunch of positive charge. So the positive charge, it's like a loose, spread out, positive charge. So that's his model of the atom. This whole thing right here you would call an atom. This teal stuff is positive charge. These little chunks right here, these are electrons that are embedded within the positive charge. Everything else is positive. Okay, so overall, this would make a neutral atom. Electrons are smaller and they're within it, within the atom. So it's all good. He called this model the plum pudding model. Plum pudding model of an atom. That's J.J. Thomson. Okay, so next, so that was a theory that was accepted for many years. How long was it actually? It was like in the late 1800s to the early 1900s. So not many years, but relative to what we think of as like change in science, it's pretty long. It's a pretty long accepted view of what the atom was like. So next came Ernest Rutherford, and in his lab he had a bunch of people firing things at atoms. So he got this very, very thin gold foil sheet. I'm not sure how he was able to get it so thin that it was only a few atoms thick. But he was able to. And so he had this sheet of gold, called it gold foil. And he was able to, maybe I can find an illustration of this. Oh, this is better. Okay. Let's see here. Yeah. Okay. We got Ernest Rutherford. Okay. Here is a great example of it. So what he did is he had, actually I don't think it was uranium. It was a different kind of, it was actually radium. This is incorrect here. It was radium that was fired in. These alpha particles, which are just, for now, you can think of them as like little tiny bullets. They're positively charged. So just little positive charges were shot at this gold foil. It's very thin gold foil. And what Rutherford thought would happen was that if you this is a little cross section of what we just saw there. If you shoot alpha particles, which are positive particles, if you shoot these particles at this gold foil, at these kinds of atoms, the positive will not be repelled by this positive charge because this is a very loose, diffuse positive charge. This positive charge will go right through this atom. At least that's what he thought. It would just go right through it. No problem whatsoever. All these would go straight through it. And it would be like just like Swiss cheese, because this is like tissue paper compared to these guys over here, which are like bullets. It's like bullets ripping through tissue paper. They would not be repelled because it's so spread out, according to this model. But then, to his surprise, I hope they show this in this little video. To his surprise, oh, there it shows going through it. But his surprise, oh my God, some of them bounced back. That's crazy. Some of those little particles, they bounced back from the screen. They deflected from that screen. And what did that mean? That means that something must be deflecting it. Right? I hope. So that must mean that inside here in that gold, there must be something deflecting these atoms, or these positively charges, back. And this didn't do the trick. So what Rutherford said is, yeah, screw all this loose positive charge out here. What's really going on is that this loose positive charge is concentrated at the very center. I'm going to call that center, I'm going to call it the nucleus. Yeah, that sounds good. So all that positive charge is in the nucleus. And we still got those electrons in an atom, but instead of them being out like that, they're instead orbiting. This is just pure hypothetical reasoning. Didn't have much proof to show this, but he thought, yeah, that makes sense. These things are orbiting this positive center here because he took his inspiration from the planets and he called this the planetary model of an atom. Okay? So again, these particles did not all rip through here. Some of them bounce back, and that's consistent with this. If you have atoms that are made up like this, most of the positive charge is not going to even hit this nucleus. It'll go right by it. But sometimes it bounces off. And when it bounces off, it's going to come back as if it hit something very massive. And that makes sense. So those are the two models so far. Now I'm going to go on to the last model, which is Bohr, the Bohr model of the atom. It can be explained in much more detail. I think I have another video up there showing it in much more detail. But the basic idea of it is that you've got the nucleus now, and now we've got the neutrons inside here in the nucleus. But now you also have electrons, and they're not orbiting. They're in shells, but we call these shells orbits just to make it confusing. So these electrons now are in shells. There's one shell. Let's draw another one. They're at different distances from the nucleus. This is the Bohr model of the atom, and I'm not going to even tell you what the last model of the atom is. And in this Bohr model of the atom, electrons can be excited and they can go up to another energy level, or shell, or orbit, whatever you want to call it, or they can go back down. But they never exist in between these shells. They just pop in and out of existence here to there, or there to there. When they go up, they have to absorb energy, and when they go down, they release energy. And that explained a whole bunch of phenomena. So this is the Bohr model of the atom. The phenomena it explained were these atomic spectra. When they excited atoms, they saw that these atoms gave off certain wavelengths of light, and those wavelengths corresponded to these electrons jumping up and down these shells. It's a very elegant model of the atom. Turns out not to be completely correct. In fact, it only really works for hydrogen. So we went on to a different model of the atom, but we're not even going to talk about that in this class because it's really beyond the scope of our class, beyond introductory chemistry. We can do everything we need to do with this Bohr model of the atom. So that's that. I hope it made sense. That's a little brief history of atomic theory.